Here's a question that sounds stupid until you actually try to answer it. Why is the Earth round? Not how do we know? We'll get to that. I mean, why? Why did nature vote for sphere instead of cube, pancake, or a giant space potato with continents glued onto the lumps? The easy answer is gravity. And sure, that's technically correct, but that's like answering, why is the cake sweet with the kitchen? Technically true, explains nothing. Gravity isn't one simple down arrow. It's a rule that quietly built every planet, moon, and star you've ever seen, and by the end of this video, you'll understand exactly how. So stick with me, because today we're covering why big things in space turn into balls, why small things stay ugly and lumpy, why Earth is secretly a little squashed, and how one guy with a stick, no rocket, no satellite, measured the size of the entire planet over 2,000 years ago. Quick honesty check before we start. If I asked you right now why the Earth is round, could you actually explain it? Not recite it. Explain it. If your answer is, gravity, followed by silence, don't worry, that's basically everyone. Let's fix that in the next 18 minutes, because nothing forced the universe to make round planets. We could have ended up on a cube Earth, tripping over corners crossing every border, or a pancake Earth, flat and syrupy, or my personal favorite, a donut Earth, where the equator is just missing. None of that happened. Round one, every single time. That's suspicious enough to investigate. If questions like this keep you up at 2 a.m. scrolling Wikipedia, you're exactly who this channel is built for. Hit subscribe, and let's get into it. Most of us grow up thinking gravity means down. Drop your phone, it falls down. Drop toast, it falls down. Butter side first, obviously, because the universe has a sense of humor. So we assume gravity is a direction. It isn't. Down isn't a real direction in space at all. Down simply means toward the center of whatever is pulling you. Stand in Mumbai, and down points one way through the planet. Stand in Mexico City, down points a totally different way. You're both right. Neither of you is about to fall off, because gravity pulls you toward Earth's center of mass, not toward some universal floor. Now rewind the clock about 4.5 billion years. There's no Earth yet. No oceans, no mountains, no Mondays. Just an enormous spinning disk of dust, ice, gas, and rubble swirling around a newborn sun. Looks chaotic. It is chaotic. But hidden inside that chaos is one very strict rule. Every single piece of matter pulls on every other piece of matter. You have gravity. Your phone has gravity. That biscuit crumb on your desk is technically pulling on you right now. Relax. It's not winning. The pull is absurdly small. But give it billions of years and billions of particles, and absurdly small starts adding up in a big way. Here's where it gets fun. 2 dust grains bump into each other and stick. That little clump now has slightly more mass, which means slightly more gravity, which means it can pull in a few more pieces. Bigger clump, stronger pull, more material grabbed. It's the original get-rich-quick scheme, except the currency is rock and ice instead of money. At first, none of this is elegant. These early clumps are ugly, lumpy, the kind of object only a geologist could love and still call interesting. Small asteroids today still look like smashed potatoes, dented and cratered, because their gravity is far too weak to fix their shape. This is really a fight. Material strength versus gravity. A small rock can afford to stay lumpy because its own gravity is too feeble to crush its bumps flat. Your house, thankfully, doesn't slowly collapse into a ball overnight. Steel and concrete beat your house's tiny gravity, easily. Explaining a spherical kitchen to your landlord would be a whole other video. But keep adding mass, more rock, more ice, more debris crashing in. Eventually, gravity gets strong enough to simply outmuscle the material. The high points get dragged down. The low points get filled in. Slowly, stubbornly, the object relaxes into the one shape gravity actually prefers. And what shape does gravity prefer? A sphere. Because a sphere is the only shape where every point on the surface sits exactly the same distance from the center. Gravity pulls inward from every direction at once, like millions of invisible hands squeezing the object into perfect balance. Picture a giant blob in space. If one side bulges too far out, that extra material is now farther from the center, and gravity keeps tugging it back inward. If one side sags low, material shifts to fill the gap. Given enough mass and enough time, the whole object evens out, not because it's trying to look pretty, because physics is bossy, and it doesn't take requests. You can actually see a tiny version of this trick right now, on Earth. Astronauts on the space station release a floating blob of water, and it pulls itself into a near-perfect little ball. That's not water attending planet school. It's the same principle. Forces pulling a surface into the most balanced shape possible. Scientists have a delightfully dry name for this balance: hydrostatic equilibrium. Sounds like a phrase invented to make you regret opening the textbook. But the idea is simple. Gravity pulls inward, internal pressure pushes outward, and when the two forces finally agree, the object settles into a round shape. There's no single magic size where an object instantly unlocks roundness. It depends on what it's made of. Ice reshapes easily, so icy bodies round out at smaller sizes. Rock is stubborn and strong, so rocky bodies need more mass before gravity wins the argument. But roughly speaking, once an object crosses a few hundred kilometers across, gravity usually wins, and the object rounds out. Below that threshold, potato. Above it, ball. This is exactly why the solar system is littered with lumpy asteroids that never got the memo. Take an asteroid like Eratosthenes. It looks less like a planet and more like a shoe that lost a fight with a hammer. It's simply too small. Its gravity could never outmuscle its own rock, so it keeps its craters, its dents, and its deeply weird shape forever, with zero consequences. Earth had no such luck. Earth is enormous, nearly 13,000 kilometers across. Stack that much rock and metal together, and gravity becomes absolutely relentless. Mountains look impressive standing at the bottom of them, but compared to the whole planet, even Mount Everest is a barely noticeable wrinkle. If you shrank Earth down to the size of a classroom globe, Mount Everest would be thinner than a single grain of sand glued to the surface. You genuinely would not feel it under your finger. That's how total gravity's victory really is, at planetary scale. So here's the rule so far. Big enough object, given enough time, gravity always wins, and round is simply what enough gravity looks like. The Sun is round for this reason. Jupiter is round for this reason. Every planet you've ever seen a photo of, round, for exactly this reason. Now, plot twist. And I did warn you this was coming. Earth is not actually a perfect sphere. I know. We just spent 10 minutes building trust, and I'm already walking it back. Earth is very slightly wider at the equator and very slightly flatter at the poles. The technical term is oblate spheroid, which sounds like a minor villain who corrects your grammar in the group chat and then blocks you. The cause is spin. Earth completes a full rotation once every 24 hours, and anything that spins wants to fling its outer material outward. You've felt exactly this on a merry-go-round, when your body suddenly becomes extremely interested in holding on tight. The equator is the fastest moving part of the entire planet, because it has to trace the biggest circle every single day just to keep up with the spin. So the equator bulges outward, just slightly, from that extra push. Specifically, Earth measures about 43 kilometers wider through the equator than pole to pole. That sounds massive, but on a planet this size, it's subtle. We exaggerate it in diagrams purely so human eyes can actually notice it exists. So Earth's real shape is a compromise. Gravity says, sphere, please. Spin says, maybe more of a pancake. And Earth quietly replies, let's just meet in the middle, resulting in a shape that's almost perfectly round, just a little wider around the waist. Deeply relatable, honestly. And if we're being painfully precise, Earth isn't even a clean, oblate spheroid. It has mountains, ocean trenches, and uneven density hiding underneath the crust. Scientists model Earth's true, messy gravitational shape and call it the geoid. Still round overall, just round with a lot of unfiled paperwork. Okay? Second big question. How do we actually know Earth is round? Because from your window, it looks flat. From your street, flat. From your rooftop, still flat. That's simply because you are unbelievably tiny compared to the planet you're standing on. A tiny ant walking across a beach ball would also swear the surface is flat. From its perspective, the curve is too gentle and too large to notice. You are that ant. Earth is that beach ball, just scaled up by several trillion. Proof number 1. Ships disappear bottom first over the horizon. Watch a ship sail away on a clear day. The hull vanishes first, then the deck, then finally the mast tip. It doesn't shrink evenly, the way it would on an endless flat surface. The ocean itself is curving away and swallowing the lower half first. Proof number 2. The sky itself changes as you travel. Certain stars visible from the southern hemisphere are completely invisible from the northern hemisphere, and vice versa. If Earth were one flat stage under a single giant sky dome, everyone on the planet would see the exact same stars. We don't, because your viewing angle changes on a curved surface. Proof number 3, and this one is genuinely elegant. During a lunar eclipse, Earth passes directly between the sun and moon, casting its shadow onto the moon's surface. That shadow is always curved. A flat disk could maybe cast a round shadow from one lucky angle. A sphere casts a round shadow from every single angle, every single time. Proof number 4. Sailors and pilots have circumnavigated the globe for over 500 years, traveling continuously in one direction and arriving back exactly where they started. On a flat map, that journey makes no sense whatsoever. On a globe, it's the most obvious thing in the world. Proof number 5. Foucault's pendulum. Hang a heavy pendulum from a tall ceiling, set it swinging, and over hours its swing path slowly rotates. Not because anyone touched it, but because the floor beneath it is slowly turning with a spinning, spherical Earth. It's basically the planet snitching on its own shape. Proof number 6 is almost insulting in how simple it is. It comes from a man named Eratosthenes, a Greek scholar working in the Egyptian city of Alexandria, roughly 2,200 years ago, long before telescopes, satellites, or airplanes existed. He heard that in the city of Siam, at local noon on the summer solstice, sunlight shone straight down a deep well, and a vertical stick cast almost no shadow at all. But on that exact same day, at that exact same time, a stick in his own city of Alexandria cast a very clear, measurable shadow. If Earth were flat, and sunlight arrives in parallel rays, both sticks should have cast identical shadows. They didn't. Which means the ground beneath those two cities wasn't lined up the same way relative to the sun. And the simplest explanation for that is that the ground between them was gently curving. So Eratosthenes measured the angle of that shadow precisely. Then he estimated the distance between the two cities, using the travel time of camel caravans, of all things. With that angle and that distance, a little geometry gave him the circumference of the entire planet. Not the size of his city, not the size of Egypt. The full circumference of planet Earth, calculated with a stick, a shadow, and some patience, landing shockingly close to the number satellites confirmed today. That is, respectfully, the most low-budget science flex in human history. And today, of course, we have the ultimate proof. Actual photographs of Earth from space, taken by actual astronauts, showing an actual curved horizon with your own two eyes. But I like the stick better. The stick had way less budget and still won. A few strange side effects of all this. Fun fact 1. You weigh very slightly less at the equator than at the poles. 2 reasons team up for this. The equator sits farther from Earth's center thanks to the bulge, and the spin itself gives you a tiny outward push. Same body, technically different number on the scale. Fun fact 2. Mount Everest is the highest point above sea level, but it is not the point farthest from Earth's center. That title belongs to Mount Chimborazo in Ecuador, because Chimborazo sits almost exactly on the equatorial bulge. Everest wins one trophy. Chimborazo quietly wins a completely different one. Fun fact 3. Not every round object in space is a planet. Many large moons are round too, including our own moon, plus Jupiter's moon Europa and Saturn's moon Titan, simply because they cross that same size threshold and gravity did its usual job. Fun fact 4. Pluto is round, despite constantly getting mocked for losing its planet status. Roundness was never the issue. Pluto has more than enough gravity for that. It got demoted for a completely different technical reason, which is honestly a whole separate, very petty video. This one rule really is everywhere. The sun is round. Every star you've ever seen a photo of is round. Jupiter, Saturn, Venus, Mars. Round, 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 round. Big enough object, and gravity simply does not let you keep a silly shape for very long. But then galaxies show up and completely ruin our tidy little rule. If gravity forces big things into balls, why does our own Milky Way look like a flat, spinning cosmic pizza instead of a sphere? The short answer involves rotation, and something physicists call conserved angular momentum, which basically means spinning things resist changing their spin. The long answer is genuinely a whole separate video, because galaxies are where simple explanations go to sweat. So here's the complete story, start to finish. Earth is round because gravity pulls matter toward the center from every possible direction. Small objects stay lumpy because their material strength beats their own weak gravity. Big objects simply cannot win that fight. Add enough mass, give it enough time, and gravity smooths everything toward a sphere. Earth isn't a perfect sphere because it spins, so it bulges slightly at the equator and flattens slightly at the poles. And we know all of this is true because of vanishing ships, shifting stars, curved eclipse shadows, a swinging pendulum, real satellite photos, and one legendary stick experiment from over 2,000 years ago. Science doesn't always need a billion-dollar rocket. Sometimes it just needs one curious person asking, "Wait, why is that shadow different?" Next time someone tells you the Earth is round because gravity, you now get to say, yes, but also material strength, hydrostatic equilibrium, rotational bulge, and a Greek guy with a stick. Then enjoy watching them regret starting the conversation. And now I've got a question for you. If gravity forces big things into balls, why are galaxies flat? Drop your best guess in the comments. The real answer is weird, beautiful, and slightly pizza-shaped. Subscribe for that one next, and as always, stay curious.